Hello and welcome back to AP Psychology. I'm Miss Lee, and in this video we are starting Unit 2, Biological Bases of Behavior. Today's video is on the neuron. Our learning targets are basically self-explanatory, no shock here. We're going to talk about the basic processes and parts of the neuron, as well as how neurons transmit messages. So if you haven't done so already, go ahead and grab your notes and let's get started. Okay, so some of this is going to be review for some folks. If you've taken biology, you've probably learned some things about the neuron. That is okay. So let's talk about what is a neuron. A neuron is a nerve cell, plain and simple. We have them all through our body. We're going to talk about the ones that are specific to psychology. So we're going to be talking about the nervous system neurons. So let's go ahead and get started with the parts of the neuron. As we're going through, I want you to, you're labeling in your notes, write down the name of the part as well as the purpose, so what it does. I'm also going to teach you a little dance as we go through, and I hope to see everybody doing this during assessment time. All right, so first off, we have the dendrites. Some of you have maybe heard me do the dendrite voice. It is basically dendrites! And I want you to do that. It will help you remember that the dendrites are the ones that receive the incoming message. It's the part of the nerve that's grabbing for the message from the nerve before it. The cell body, it contains the nucleus. It is the body of the nerve, okay? So if you have your dendrite here, I want you to kind of bring it close into yourself, and it is going to basically bring the message into the soma, your body, okay? It's going to bring it in. The cell body, or the soma, contains the nucleus. It is the largest part of the nerve. And the nucleus makes the decision whether or not to fire. It's going to make the decision about whether it's going to send the message on down the neuron to the next neuron. And how you can remember that is sometimes people make decisions with their heart. So you can kind of pretend that your heart is the nucleus, okay? So we've got our dendrite, we've got our cell body, and we've got our nucleus, okay? Now, the longest part of the nerve or the neuron is the axon. It's the longest part, and this is the part where it's actually going to have the electrical message travel. So the message that's being sent through the neuron is actually going to travel down the axon. So what I want you to do is I want you to extend your other arm, okay? So you've got your receiving dendrites and you've got your axon, okay? You've got your axon and it's the one that's going to send the message. All right, on the axon, you've got these, they look like sausages to me, like old-fashioned, you know, when you see the cartoons and the dogs running off with the sausage. It looks like that to me. That's what the myelin sheath looks like. This is fatty tissue that insulates the axon, and what it does is it speeds up the transmission of the message. It's like if you have repaved a highway, and I always think of the axon as the highway. If you repave it with beautiful new blacktop or like just gorgeous new road, you can travel faster on it, can't you? So that's the way I think of myelin sheath. It's just a really delightful, new, beautiful blacktop that you can travel really fast on. And it looks kind of like, to me, sausages. But I want you to pretend, if you've got your arm extended, that it's like those armbands from the like 80s and 90s. So they're sweatbands, and even though we only wore one at a time, we're going to pretend that we're wearing more than one, and they're just all lined up the arm, okay? And it helps the message to go faster. So you've got your dendrite, you've got your soma, you've got your nucleus, now you've got your axon with the pretend myelin sheath. The space in between is called the node of Ranvier. It's the space between the myelin sheath. That's all it means. It's named after the guy who figured it out, Ranvier. And the little dot in the middle is representing Schwann cells. These are non-neuronal cells in the central nervous system, that's the CNS, that form the myelin sheath. So that's all it does. It's not technically part of the neuron. All it's doing is like a factory building the myelin sheath. And at the very end, okay, at the very end is your axon terminal buds. This is the end point of the neuron that releases the neurotransmitters. The neurotransmitters, and we're going to get to that, are the chemical messages that are being sent across the synapse to the next neuron, okay? You've got your dendrite, you've got your soma, you've got your nucleus that's going to decide, because sometimes you decide with your heart whether to send the message down the axon, and it's going to leave through the axon terminal buds, okay? We're going to get a close-up of what that looks like in just a second. All right, so that's your dance. That's your neuron dance, okay? All right, so there are different parts of the neural firing process that you need to be aware of, and I don't want you to get scared here. This is very sciencey, it's very biology, and I don't want you to get too lost in this process. So first, you start with a resting potential. This is when the neuron is not firing. It has a mostly negative charge and mostly potassium ions inside and mostly sodium ions outside. That doesn't mean there aren't potassium ions outside and sodium ions inside. It just means that there is a much greater percentage of potassium inside and sodium outside. This is the resting potential. This is where the neuron really likes to be, the status that it really prefers, okay? It's when it's not firing. It's ready to fire, but it's not firing at this point. This means that the neuron is polarized when the opposites are away from each other. That's what polar opposite or polarized means. It means that the opposites are pushing away from each other. They don't like each other. And so sodium and potassium do not like each other. So at resting potential, the neuron is polarized. It's when sodium is on the outside, potassium is on the inside. Again, there's a little bit of the other also, but it's really pushing away from each other. It doesn't like it. At this state, the neuron is at what we call homeostasis. And this is a word that you're going to hear a number of times during psychology because we use it for different purposes. It's the normal happy resting state. It likes to be at homeostasis. It's going to try to get back to homeostasis as hard as it can. That's what it wants to do. With action potential, which is another word for nerve impulse, the electrical pulse or message travels the length of the axon. This is, again, part of the neuron firing process. Action potential is just another word for nerve impulse. It only goes one way. A principle that you need to understand about how neurons fire. And we're going to go on a little field trip in just a second. The all or nothing principle is very important to remember. It's when the nucleus decides to fire, it fires down the axon completely, all the way, or not at all. When the nucleus decides to fire, it's either going to do it all or nothing. It's the all or nothing principle. And at the same time, the intensity is going to stay exactly the same. It does not lose intensity as it's traveling down the axon. The strength or the power of the message is going to continue all the way down the axon and out the axon terminal buds. So based on your knowledge of the neuron so far, I want you to consider how it's similar to a toilet. In fact, I want you to pause the video right here, and I want you to take a little field trip wherever you are. I want you to travel away from your space right here, go down to the nearest restroom, wherever that is. I want you to very scientifically flush the toilet. Press down the lever or the button or whatever makes the toilet flush, and I want you to think about, as you're doing this, how that is similar to a neuron firing. How are these two similar? Are you back? I want you to go ahead and jot it down. How is a toilet flushing like a neuron firing? We're going to talk about it in class. So let's talk about when the neuron actually fires. Up to this point, it has not fired. It's been at its resting potential. It's been at homeostasis. Let's say the nucleus has decided it's going to fire. Depolarization is when opposites are no longer away from each other. They are no longer polar opposites. So this happens when the action potential begins. It happens like a domino effect. If you've ever seen one of those like those really intricate domino setups, and it starts and it's like boop, 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 it goes down and around. It doesn't all happen at once. The dominoes don't all fall at once. It happens one at a time, but once it starts, it continues. You're not able to really stop it. So when the action potential starts, sodium ions rush in from the outside of the axon, and potassium ions rush out. This is called depolarization. At this point, after the action potential has traveled the length of the axon, there's going to be what's called a refractory period. This is a period of time after the firing that the neuron is focused on resetting. It's trying to get back to homeostasis, and it's not able to fire again. It can't do that, okay? So what is happening is that the sodium is going back out, and once the sodium goes back out, the potassium feels good about coming back in. Remember, they don't like each other. They are polar opposites. They don't like each other, so the sodium has to go back out in order for the potassium to feel good about coming back in. So during the refractory period, everything is resetting. It's getting back to normal. So sodium goes out and the potassium can come back in. All right, so again, write down in your notes, how is the refractory period similar to the process of a toilet flushing? Pause here, jot down your thoughts. Do you have it? I'm going to go ahead and give you a hint. If you have just flushed a toilet and it has flushed and everything has gone down the axon, hopefully your plumbing is working fine because it should only be a one-way street, right? Am I right? Once you have flushed, you can't reflush until it is reset. So that is like a refractory period. The toilet is filling back up, the tank is filling back up with water, and you can't reflush. Okay, so we're going to go back through this once again. And this isn't to complicate things, this is to clarify. We're going to pretend that we're looking at an axon. So this guy right here, it looks like a negative sign, and I want you to think about it that way. In its resting potential, a neuron is negatively charged, okay? In its resting potential, in its homeostasis, a neuron is negatively charged. When the action potential starts, the sodium channels, these little guys right here, okay, we're looking at these. These are channels. They're like openings. The channels open and sodium ions rush in. So it's almost like it gets sucked in, all right? So it starts with the stimulus. This is the action potential starting down the neuron. The sodium channels open up, sodium ions rush in. Potassium is having none of it. Potassium does not like to be in the same area that sodium is. But the potassium channels open and potassium rushes out. So as this is happening down the axon, remember the neural firing happens down the axon. The action potential travels like a domino. As this is happening, it's causing one to open, one to open, one to open, and it keeps going down like dominoes. So at the very beginning, once everything is fired and everything is cattywampus, everything is mixed up, the first sodium channels close, but the channels further down the axon start to open, causing the process to continue down the length of the axon. If you have any questions, go ahead and jot them down. You are going to have a video to watch. I will share that with you in class, just about the sodium, potassium. It's called a pump. All right, so let's talk about the synapse. So we've got another viewpoint of the end of one neuron and the beginning of the next neuron. So this is the tip of a dendrite. This is an axon terminal bud. So we know that the action potential goes in one direction. The arrow here that you see on your screen is demonstrating that the action potential is going to travel down this neuron, and as it does, it's going to send messages to the axon terminal bud to send out the neurotransmitters that the message is telling the axon to release. The neurotransmitters are the chemical substance that cross the synapse to carry the message to the next neuron. It's going to cross the synapse. This is the synapse right here. All a synapse is an open space between the two neurons where the neurotransmitters cross. It's not part of the firing process. It's not part of a neuron. It's the space in between, and it's microscopic. You wouldn't be able to see it with your, with your naked eye. You would have to look at it through some type of very strong microscope. But it is a space, it's a gap between. Sometimes it's called a synaptic cleft or a synaptic gap because that's what it is, it's a gap. So on the receiving neuron dendrite, there are receptor sites. These are specific points on the dendrites of neurons that receive specific types of neurotransmitters. It is very much like a lock and key, and we're going to move with that analogy as we go through this unit of study. Again, the synapse is simply a gap. It's an open space between the neurons. It's not part of the firing process. This is super important for you to remember. We talk about a handful of neurotransmitters, and remember, the neurotransmitters are those tiny little dots. They're the chemical substances that cross from one neuron to the next neuron to tell it what kind of a message to send. So let's talk about the specific types. We only talk about a handful in psychology, although there are over 100 that we know of. Acetylcholine is the first one that we're going to talk about. It is important in muscle contractions, in memory, and in learning. And I'm also going to explain some of the associated disorders with the neurotransmitters. Alzheimer's disease is a big one that is associated with acetylcholine. So basically, if you have too little acetylcholine being sent across the synapse and received by the receiving dendrite, you could end up with Alzheimer's disease. That's how it would kind of show up. Dopamine is a very important neurotransmitter, and it's indicated in a lot of conditions that we look at in psychology, and it has several roles. Movement, thought processes, and you see the next words are bolded. This is really, really important. The rewarding sensation. So when you eat your favorite meal, when you ask somebody out and they finally say yes, it's anything that makes you feel pleasure, okay? If you have too little, you could end up with Parkinson's, too much, schizophrenia, and this is also very much indicated in not only drug addiction, but really any kind of addiction. So the next neurotransmitter is serotonin, and we're talking about emotional states, sleep, so the cycles of sleep, and too little serotonin being sent across the synapse and being received by the next neuron could indicate depression. Norepinephrine, its primary roles are physical arousal, learning, and also memory. And depression and stress are some of the associated disorders. GABA, its primary role is inhibition of brain activity. So think about what types of disorders might be problematic if you don't have an inhibition of brain activity. Anxiety disorders, okay? And then last but not least, endorphins, primarily related to pain perception, positive emotion. It's that runner's high. If you have ever gotten a runner's high, or even if you have maybe gotten an injury during sports and didn't realize it later, it's because of the endorphins that were released. And one of the big disorders that is associated with endorphins is opiate addiction. All right, so let's talk about agonists versus antagonists. Okay, people get confused about this, and I don't want you to. Remember, I told you we were going to come back to that key analogy. All right, so the first thing to understand about agonists and antagonists is they are both external substances. This is something that we are introducing to our system that is not naturally occurring. However, it is important to also remember that these agonists and antagonists would not work, they would not have the effect that they have if there wasn't already something naturally existing in our body that it didn't look like or do something like, okay? Don't get confused. So both are outside substances that somehow interact with neurotransmitters at the receptor sites. So you're thinking about the dendrite of the receiving neuron, okay? Something is amiss, something is happening, okay? And both interact differently at the receptor sites. So let's dig in. If we are continuing with our key analogy, you have a house key, which is a key that is designed specifically for a lock. You may have a master key, which will open all the locks in your house, all the locks, maybe even at the school. So like at our school, I have a lock, I have a key for my lock. I can't open any other door with that key. However, the custodians have a master key so that they don't have to dig through all of their keys to find my door lock key, they have a master key and it opens everything. And then, now this I'm going to have to ask you to go with me on this. There's a fake or a wrong key, and it's going to fit sort of, but its primary purpose is to block everything else, okay? So let's keep going. All right, agonists mimic neurotransmitter activity. They do something really, really similar, okay? So basically, an agonist fits in a receptor site. It works like the original key, but it doesn't do exactly the same thing, okay? Antagonists block neurotransmitter activity. So it's fitting in the receptor site, sort of, but basically what it does is it prevents the real neurotransmitter, the house key, from getting to its receptor site and doing its job. So it's basically like putting a stick in and breaking it off into a lock. So you can't put a key in, it's blocked. You can't fit the house key in anymore. All right, so examples of this. Morphine. Morphine is an opiate derivative. It comes from the opium plant and it mimics endorphins, and it mimics endorphins really well. So well, in fact, that we have an opiate addiction crisis in America right now. So think about the effects of morphine. What does it do? Well, it acts like an anesthesia. In fact, morphine is a painkiller. It's an anesthesia. But how does that make sense given the role of endorphins? One of the things that endorphins will do, besides give a sense of pleasure, it will also reduce pain. So if you are running and you twist your ankle, but you want to finish the race, you keep going, you didn't realize you sprained your ankle until after the race is over. Well, that's because of endorphins. Endorphins have kicked in, you've got that runner's high, and it is acting like an anesthesia. Antagonists, what they do is they block the neurotransmitter. So it's going to fit in the receptor site so that you can't get the house key in, all right? Let's talk about Botox. Botox is a form of botulism. Botulism is an antagonist. It is going to block acetylcholine. And if you think back a couple of slides, what is the role of acetylcholine? Well, its primary role is movement and memory. And if you are familiar with what Botox does, you basically get injections, usually in your face, and it prevents you from being able to frown or make wrinkles in your face anymore because it's blocking the neurotransmitter acetylcholine in that specific site from allowing movement. So that's why you see people like this with Botox. I'm so very happy right now. I'm smiling. Well, they can't move their face. Their muscles have been paralyzed from the form of botulism that has been injected into their face that's blocking acetylcholine. It's blocking it at that site. So if you've ever gone to the grocery store, you've gone to like Piggly Wiggly or Kroger, and maybe you've ever been told not to buy a can that is dented. Well, it may be that someone just dropped it and put it on the shelf, but it also could be that the food inside the can contains botulism and it's acting like a vacuum, pulling the can inward and denting it. And if you eat food that is contaminated by botulism, it's going to paralyze or stop your digestive tract from working. It's going to block the acetylcholine in your digestive tract and it's going to paralyze your digestive system. Well, that is not good. And you would likely die if you weren't around an ER very quickly. So make the connection. Hopefully you're making the connection that Botox, botulism, it's blocking acetylcholine. It is an antagonist. And that is it for this video, neurons and neural firing. In our next video, we're going to be talking about the nervous system. I can't wait to see you then. Bye for now.